Hello student, welcome back. It is Module 5, Lecture 4. It is the last lecture of Microcontroller and Embedded System. Sangita Roy, Assistant Professor, Electronics and Communication Engineering Department, Narula Institute of Technology. Elementary idea on robotics. Lecture 4, Semiconductor Displacement Sensor. In the previous class, we have studied robotics, brief history of robotics and different terminology in robotics, and especially in lecture 3 we have studied the limit switch, proximity sensor limit switch. Today we will discuss about displacement sensor and semiconductor displacement sensor. Introduction. What is a displacement sensor? A displacement sensor is a device that measures the distance between the sensor and an object by detecting the amount of displacement through a variety of elements and converting it into a distance depending on what element is used. There are several types of sensor such as optical displacement sensor, linear proximity sensor, and ultrasonic displacement sensor. What is a measurement sensor? A measurement sensor is a device that measures the displaced dimension of an object by converting changes in amount of light into electrical signals when the object interrupts a white laser beam. Features. A physical quantity of an object can be measured. A displacement sensor measures and detects changes in a physical quantity. The sensor can measure the height, width, thickness of an object by determining the amount of displacement of that object. A measurement sensor measures the position and dimension of an object. Physical quantity output is also possible in addition to on-off signal output. An analog output of physical quantities, current output or voltage output can also be performed excluding some models. Some models also support digital serial communication. Operating principles and classification. Displacement sensor, optical displacement sensor, triangulation measurement method. Three sensors used a triangulation measurement system. Some sensors employ a PSD and other employ CMOS CCD as the light receiving element. And this figure shows the model. PSD method. Light from the light source is condensed by the lens and directed onto the object. Light reflected from the object is condensed on a one-dimensional position sensing device PSD by receiving lens. If the position of the object, the distance to the measuring device changes, the image formation position on the PSD will differ and the balance of the two PSD outputs will change. If the two outputs are A and B, calculate A divided by A plus B and use appropriate values for the span coefficient K and the offset C as shown below. Displacement is equal to A divided by A plus B into K plus C. PSD full form is position sensitive device. CMOS CCD method. Compared with the sensor that employ the PSD method, the sensor that employs the CMOS CCD as the light receiving element provides a more accurate measurement of a displacement without being affected by the surface, color, and texture of objects. The sensor detects the amount of light on the individual pixels in the CMOS CCD and converts them into a distance when a spot beam that reflects off the surface of the object is projected on the light receiving element. Emitter receiver, near and far end, and the target object is showing. Basically, this is image formation model and image processing that is used over there. But details we are not discussing over there. No difference in performance. PSD method center, this is the center, and CMOS CCD method, this is the center and this is the peak value. When the variation in the surface color and texture of the object within the laser spot are negligible, there is no difference in accuracy between the two methods. When performance error occurs, PSD method, when the variation on the surface, color and texture of the object within the laser spot are considerable, the center position of the light and the true peak position are offset with the PSD method. The true peak position can be measured with the CMOS CCD method. Difference between CMOS and CCD. CCD stands for charge coupled device and CMOS stands for complementary metal oxide semiconductor. Now for CMOS image sensor and CCD image sensor. Readout method. For the first case, signals for individual pixels are read out and the voltage is amplified on a pre-pixel basis. And for the second method, signal for the individual pixels are read out sequentially and the voltage is amplified at the end. Advantages. For the first method, power consumption is small, that is for CMOS method, image sensor method, power consumption is small, faster operation is possible, processing circuit can be integrated with the sensor. For the second method, CCD image sensor, image quality is very good, and as the technique or technology is improving, the image quality is excellent. Disadvantage. Image quality for CMOS method varies between individual pixels. Sensitivity is approximately 1/5 of that of a CCD. Whereas in case of CCD image sensor, power consumption is large, faster operation is difficult, manufacturing process are complicated and high cost, but image quality is very good. Regular reflection model and diffuse reflection model. Regular reflection and diffuse reflection. For the case of regular reflection, a specular reflection is produced such as from a mirror surface or glossy objects, and for diffuse reflection a beam is reflected in all directions from an object with a standard surface. Regular reflection model, from the light, object is directly received by regular reflection and stable measurement is possible of the metal and other objects with a glossy surface. In case of diffuse reflection method, a light beam is projected perpendicularly onto the surface of the object and the diffuse light that is reflected back is received for a wide measurement area. This is the figure. Regular reflective sensor heads receive direct light from the regular reflection of the object. Stable measurement can be achieved for objects made of metal or other materials with a glossy surface, but there is a narrower measurement range than diffuse reflective sensors. Diffuse reflective sensor use a sensor head tilted at an angle to receive the regular reflection light. This allows the sensor head to be placed at a distance away from the object. This is the figure showing over there. Regular reflective sensor head and example of diffuse reflective sensor head tilted at an angle. Line beams and spot beam. Line beam model. This model measures the average displacement within a line beam. Depending on the measurement condition, this model provides stable measurements without being affected by bumps or unevenness on the object surface. Moving direction. Line beam reflected in a CMOS displacement direction is showing over there. Spot beam model. This model is more susceptible to the influence of bumps or unevenness on the subject surface. So this is the moving direction. In the horizontal direction, left and right, it can move, and displacement direction up and down over showing over there. Now the control principle. Based on the confocal principle, the emitted light and received light are positioned along the same axis. Light is received only when it is focused on the measurement object, allowing the height to be calculated. The received light waveform is not disrupted by the material or inclined of the measurement object. The received light waveform is always stable, which enables high resolution measurement. Object located at focal point, object not located at focal point, and inclination and differences in materials. These three types is showing over there. For the first case, object located at focal point. The reflected light is focused at the same point as the emitted light. The reflected light becomes the received light signal. The height is calculated from the position at which the reflected light was received. Object not located at focal point. Reflected light is not received because the reflected light is not focused at the light emission point. Inclination and differences in materials. Even if the measurement of the object is inclined or contain different materials, the reflected light will be focused at the light emission point as long as the measurement object is at the focal point. So it is shown over there, the light position, focal point. So it is tilted, and at the output it is showing white light confocal principle. White light confocal principle. The white light from the LED is focused at different points for each color, that is to wavelength, due to a special set of lenses in OCFL module in the sensor head. As a result, only the color of the light that is focused on the measurement object is returned, allowing the distance from the sensor head of the measurement object to be calculated based on the color of the reflected light. The sensor head contains the special set of lenses that separates the white light into the different colors, and the controller contains the white LED light source and the spectroscope and processor that converts the color of the reflected light to a distance. There is no need for a lens, drive mechanism, or electronic parts in the sensor head. Even though they were considered to be standard in previous confocal models. This achieves is a much more compact design and much greater immunity to noise than triangulation models or previous confocal models. So height is detected based on the wavelength. The reflected light of the wavelength that was focused on the surface of the measurement object passes through the fiber, and the spectroscope in the controller converts the wavelength to a distance. So white LED light source is shown over there, fiber optic cable, then white light OCFL module, then it is colors are separated along the high direction, then near the far end amount of light that is received. The OCFL module contains a special lens set developed by OMRON that changes the focal point for each color of the white light. The small The spot diameter is the same as any position within the measuring range. It does not change the way it does for a triangulation. High precision lens manufacturing technology has allowed us to achieve a lens structure that is extremely small and that also does not require a drive mechanism. OCFL full form is Omron Chromatic Focal Lens. Light cutting method. The light cutting method is widely used. It is widespread. Laser beam is projected on the measurement object to measure its cross-sectional shape. A band-like laser beam is projected on the measurement object and the reflection from the object is received by CCD. A shape profile of the measurement object is formed based on the principle of triangular distance measurement. Since 2D data of the x and z axis are measured simultaneously, there is no need to move either the sensor or measurement object. So it is shown over there, the method, target object, above that the module is fixed and profile is measured. So it is linear proximity sensor showing when an AC flows through a coil, magnetic flux occurs in the coil. When the magnetic flux passes through the metal object, it creates eddy current that generates a magnetic field. We have already discussed this in the earlier class. And how it is produced, it is showing over there in detail. Then ultrasonic displacement sensor. This is differential transformer method under contact displacement sensor. This type of sensor measures displacement through the direct contact of a measured object with the sensor. It provides superior measurement precision compared with the contactless sensors. And the method is, the model is shown over there. That is displacement that is measured. There are coils and it is split into two parts, V1 and V2, coil 1 and coil 2. Center of the coil is shown over there and that is measured. The displacement is measured by this method. Magnetic sensing method. When the sensor head touches the object, a magnetic scale with north and south poles alternately positioned at a fine pitch inside the sensor moves. The changes in magnetic flux that occur at this time is detected with a magnetic resisting sensor to determine the displacement. The model is shown over there. Measurement sensor, optical measurement sensor which measure the width and position of object. Use one of the following three methods: light intensity determination, CCD, or laser scanning. Light intensity determining method, its structure, application, determining outer diameter, determining edge position. CCD method and its structure is showing over there. It determines the outer diameter, detecting edge position, determine pin pitch, detecting bar position. Laser scanning method. This method, its model is showing over there. It determines the outer diameter, detecting edge position and determine pin pitch. Now these are the method already we have discussed. The light intensity determining method, a parallel laser beam is emitted from an emitter to a receiver and is focused onto a light receiving element by a lens at the receiver. If there is an object between the emitter and the receiver, the incident level of the laser beam decreases and the center outputs the changes resulting from the width of the object as a change in a linear output. CCD method. A one-dimensional CCD image sensor is used in the receiver to recognize the position of an object. The CCD method uses digital processing, so it enables the sensor to perform more accurate measurements compared with the light intensity determination method. Laser scanning method. The laser performs measurement by emitting a laser beam while scanning a small diameter laser beam from the emitter. The sensor measures the time that an object blocks the beam as the width of the object and then calculates the outer diameter of the object. Now some terms associated with this semiconductor displacement, that is resolution. This is the width expressed in terms of the distance of the fluctuation in the linear output when the measurement object is still. The narrower the width of the fluctuation is, the better is the resolution. The concept is showing by this figure. Full scale, FS. Full scale indicates the full scope of measurement range. For example, full scale of the sensor with the measurement range of plus minus 10 millimeter is 20 millimeter. Linearity, error with respect to ideal straight line of the linear output. Normally it is percentage of measurement full scale FS and it is expressed in percentage full scale. For example, 1% full scale. Examples, linearity is plus minus 0.2% full scale. If the full scale is 20 millimeter, then plus minus 0.2 into 1 by 100 is into 20 or plus minus 40 micrometer. And it is shown in this figure. In the x-axis, it is the distance in millimeter, and in the y-axis, it is the current in milliampere. So the signal, how the signal changes or the current changes, it is showing over there. Therefore, error is showing over there, and also error for the one half it is showing over there, and in the next half it is also error showing over there. And what should be the ideal line, that is also showing like an ideal straight line. So this is the linear output. The error is showing over there. This is a concept is given over there. Temperature drift, the amount of variation of linear output with respect to changes in the ambient temperature. Normally it is a percentage of measurement range full scale, and it is expressed in terms of percentage full scale per degree Celsius. For example, 0.03% full scale per degree Celsius Fs is equal to 20 millimeter. In this case, the fluctuation in the linear output for each 1 degree Celsius change in temperature would be plus minus 0.03 into 1 by 100 into 20, that is to plus minus 6 micrometer. If the ambient temperature changes from 23 degree to 55 degree, the fluctuation would be plus minus 6 into 55 minus 23, that is to plus minus 192 micrometer. Linear output, analog output. The output of measurement results converting into a current or voltage. Therefore, in the x-axis, it is the distance measured in millimeter and the output current milliampere, that is showing over there. The change is distance and the corresponding change in current. Response time. Linear output when the displacement and the width of the object are changed to steps. If the analog output, the time required for 10% to 90% change is expressed in terms of the response time. The displacement in step and the corresponding response is showing over there. To some extent, little bit of curve over there. Therefore, linear output where it is and corresponding response is 10% to 19%. How the response changes, it is showing over there. Light receiving element. An element used to recognize a laser beam as a signal. There are various types of light receiving elements such as a PSD, position sensitive device, and a CCD charge coupled device, or a CMOS complementary metal oxide semiconductor. Static resolution. The variation width of the measurement values when the object and the sensor are stationary. These variations are primarily caused by the fluctuation due to noise inside the sensor or controller. Moving resolution. The variation width of measurement values when a flat object or the sensor itself is moving. Variation occur due to the fluctuation caused by the surface of the object during measurement in motion. The moving resolution is smaller for object with an even surface such as mirror or glass, which results in measurements close to the static resolution. The moving resolution increases for objects with a rough surface, dispersion workpieces, or objects with a surface that affects the amount of laser light reflected light absorbing workpieces. When compared with the static resolution, the moving resolution will be 10 or more times lower depending on the object. Impedance. The AC resistance when an AC current is applied to a circuit. So, we are concluding our lesson and we ending this course also. So these are the references, and thank you. We are ending microcontroller and embedded system total class, and we are ending the lecture session of this subject. Thank you.